Yes, in this video we will now take a look at some additional considerations when using AVL trees and variable size locators together. First, let's look at how to cover a case where there are data blocks of the same size in the AVL tree. I mean, let's say the memory pool is like this. Then there are blocks of data like this in different locations. But if you look closely, all of these are assignable sizes. But the starting order of this memory is different. But when we configure the AVL tree, we said that the key value is the size. But there are now data blocks of the same size. What would you do with a case like this? Let's assume for a moment that there are 3 digits here and there are also these digits. Young X what? Oh, young X, or 3 characters. Then the tree consists of these nodes of the same size as a connected list on the tree. This is what happens when you draw a picture. Now, if you go to the left, you will go to the right. I don't know the order, but oh what? There must be one like this, right? We are also implementing the connection list award here. In this way, what if young X or saying young? If there were 7 digits, what would I do in the extra data blocks on this memory plan? What would I do in 0x? If you say that Oyong was like this, these are not rods belonging to the frame, but 7 young X Oyong are attached to the right side of this rod in front. That is, data block nodes of the same size in the AVL tree, managed in the form of a linked list, but only women. At first, it means that it is recognized as a mode belonging to the 2 AVL tree. That was the first warning. Now then, I did a real test to see how fast the second one actually got. So far, theoretically. You said the memory pool is faster than a regular new delete, right? Well, if we talk about free list allocator, we theoretically said that the light size allocator is faster than this, and the version with the addition of a belt tree is faster than when I told you what the reality was. These numbers right next to me, these numbers right here, are actually the benchmarks that we were comparing. Now man, the green below is the speed with a normal udelete, and then the blue here is the speed with only the light size allocator, this orange with the light size allocator. This is the speed when you mix AVL trees. So now we're showing what the actual allocation rate is when we assign 10,000, 50,000, 100,000 classes to about 10 different sizes. Then, as you can see, contrary to expectation, contrary to theory, AVL tree. It's slowest when you use a variable size locator together. Now, because when we did inu and delete, it was really just allocation and cancellation costs. But what happened when we used this variable size allocator? There was a list of connections. So, what kind of meta information is that? The size, And now this cost of adding and subtracting this metadata containing this memory start address is additionally included. Similarly, if you use the two AVL tree together, remove inserts for this tree as well as the connected list. Because there are additional costs, it may be slower than we expected. Now, of course, it can be overwhelming to compare the three methods simply based on a certain release or allocation cost, because as we explained at the beginning, there are many main factors that use this memory leaf, but when I thought about it, I think the first criterion is to minimize this allocation and release cost, and the second criterion is to improve this cache hit rate. And because we've only done this comparison in terms of the cost of the allocation right now, we have to actually compare the data allocated through that memory pool no matter how fast we access it, to make a complete comparison. But the first thing we need to note here is that, contrary to expectations, it can be actually slower in some ways. Contrary to theory, let's just look at these two of the three. Then, as shown here, when using AVL together, it's just slower than a regular variable size allocator. So you might ask, is this useless? The important point here is that, as I said earlier, I've only tested 10 classes. What we mean by 10 classes is 10 different sizes. What work? What 2, 3, 4, 7, 8, 90. This is what we get when we try to do with 10 different sizes, but we're not actually developing an application. Really, you're going to assign hundreds or thousands of different sizes of classes using this memo DIPL, which means that we actually use the more varied the number and types of these sizes, the larger the number, the more different classes of these sizes, the 1 million, 10 million, 10,000 or more sizes of these sizes are allocated to this memory pool, then the combination of these AVLs and variable locators will improve performance. We've only used 10 here, so it may be a little slow, but we expect it to improve as we get bigger. Now, that's all for a video on additional things to keep in mind when using AVL trees and variable size locators. Next, let's talk a little more about how we actually implemented batch rendering.